All right, let's start. PDE. So the exam on Monday is just on the Laplace transform and the method of characteristics. And what I'm going to start to do today, and what we're covering in the last month of the term, are chapters 3 and 4 in the book by Logan. Chapter 3 is on orthogonal expansions, and chapter 4 is on PDEs on bounded domains. And that's what we'll be doing. So, and chapter 3 in Logan is very nicely done, and I'm going to follow it very closely starting right now. So, and okay. So let's start.
Professor.
Yeah.
So the rest of the material is going to be from the Logan textbook?
Yes, I think we're going to cover all of chapters 3 and 4 in Logan, and that'll take up the last month of the term.
Okay, thank you.
So we've already discussed quite a bit about that you find in the first part of Logan's chapter 3, but it's always good to review and cover things multiple times. So I'm just going to go straight through Logan as much as I can today. So section 3.1 is called the Fourier method, which is exactly what we saw in the book of Farlow when we separated variables for the heat equation. Partial of u with respect to t equals second partial of u with respect to x, where x is between, in this case, 0 and pi, and t is greater than 0. So the range of x is bounded. This is not over the whole line or an infinite interval on the line. So we have a bounded domain for x. And let's say we have some boundary condition, which is that at the ends, u at x equals 0 and at x equal pi, for all t, we get 0. And we saw when we separated variables, we got a family of solutions of the form u sub n of xt is equal to e to the minus n squared t sine of nx as for all positive integers n. We found this infinite family of solutions, and they all satisfy the boundary conditions, and they satisfy the differential equation. But we also usually have an initial condition. That is, at time 0, u of x at time 0 is some function of x. And we want to know, can we also satisfy the initial condition with these functions? And Fourier's idea is you can write u of xt as some linear combination of these basic functions. So this sum over n, a sub n, e to the minus n squared t sine nx, and as some convergent, this is a big theorem to prove this, but that you should be able to write a solution to the differential equation, including the initial condition, as some infinite series of constant times these fundamental solutions. And If you let t equal 0, this says that u of x 0 is equal to summation a sub n. When you let t equal 0, this is just 1. So this is an sine nx, and that has to be your function f of x. So the crux of Fourier's idea was that you should be able to write your initial condition as some combination of these sine functions. And once you do that, you have, by this formula, the solution of your partial differential equation that satisfies both the boundary condition and the initial condition. And we've seen several times the method to compute these coefficients. That is, we want to find a sequence of numbers, an, which are called the Fourier coefficients for this problem. Such that f of x is summation an sine nx and goes from 1 to infinity. And the way we do that is to take f of x and for some particular number m, multiply it by sine mx. That summation n goes from 1 to infinity, an sine nx sine mx. And then integrate this from 0 to pi. And if your function f of x is reasonably nice, you can interchange summation and integration. You get summation n goes from 1 to infinity, an, integral from 0 to pi, sine nx sine mx dx. And then you do a calculus exercise, which is for m different from n, the integral from 0 to pi sine nx sine mx is 0. So all but one term here disappears. Oops, sorry. Yeah, that's right. So we get the integral from 0 to infinity, f of x sine mx dx is just am, integral from 0 to pi. When m equals n, this is sine squared mx dx. And this integral is pi over 2. The integral of sine squared mx dx from 0 to pi is pi over 2. So this is am times pi over 2, which gives us a formula for am. 2 over pi, the integral from 0 to pi, f of x sine mx dx. So this is our standard method. I mean, by now I hope standard for solving the heat equation in this example. So long as you can calculate the Fourier coefficients. Now, the sequence of functions, sine nx, n goes from 1 to infinity, satisfy the following two properties. The integral of sine nx sine mx dx from 0 to pi is equal to 0 if m is different from n, and it's equal to pi over 2 if m equals n. And this is an example of what we're going to call an orthogonal sequence of polynomials. So okay. So I should just point out, because I want to follow in the book, section 3.2 computes the Fourier series for the following function. Suppose you take the step function f of x, which is equal to 0 for x less than 0, and 1, well, from minus pi to 0, and 1 from 0 to pi. So the function looks like this. It's just a step function. And there's a nice example, a calculation of calculating the Fourier series for f of x. Actually, of course, maybe you're not used to doing this and have never done it taking advantage of Maple or perhaps some other computer program. The Fourier series it calculates is f of x is equal to 1/2 plus 2 over pi times the sum of 1 over 2n minus 1 times the sine of 2n minus 1 times x. N goes from 1 to infinity. This just means we're only summing over the odd integers. So this is 1/2 plus 2 over pi sine x plus 1/3 sine 3x plus 1/5 sine 5x, and so forth. And so somehow these oscillating functions, when you add them up, should converge to this very non-oscillatory step function. So let's do an experiment. I want to get Maple. So okay, so I hope I'm sharing the screen with my Maple worksheet workboard. So So let me define a function. One over 2n minus 1 times the sine of 2n minus 1 x. And suppose I consider the sum of this function gn of x. N goes from 1 to 5. And I want to add a half to that, because that's the constant. So let me plot this function from minus pi to pi. Oh, look at that. Huh. Wait. Sorry, there's no half. There we are. So this is here we are. So this is the function 1. This is the function minus 1. Ah, okay. So I made a mistake. It's 2 over pi times this. And I do need a half. So that's the function. Oops, sorry, that's not the function. That's the function g over n. And I want to add one half plus that. Then this is the function I want to okay, there we go. So I don't need that. There we are. So here I've added the first 5 terms of this Fourier series plus the constant term. And I want to approximate the function, which is 0 here and 1 here. Let's take a few more terms. Let's see what happens. It gets better. Suppose I take 20 terms. Gets even better. Suppose I take 50 terms. Even better. Suppose I take 100 terms. Wow. I mean, a little bit messed up at the endpoints and here where we have a discontinuity, but it's looks pretty much like 0 and then 1. See if maybe we'll do 500 terms. Fantastic. Look at this. 0, 1, and something weird at the boundary at the endpoints. And it's not clear what is here, but that's pretty good. I mean, it is stop share. Okay. So I hope you can appreciate that. It really is a very impressive numerical and visual confirmation of what Fourier series do. How these oscillating terms can somehow cancel in a miraculous way and create this discontinuous function. Okay, so we're going to spend time with Fourier series again, but it fits into a very important context of series of orthogonal functions. So suppose we have a space or a set of functions defined on an interval from A to B. So this is a bounded closed interval. And they can be continuous functions, differentiable functions, piecewise continuous, anything that you're used to using. And I want to define what is called an inner product of functions f and g. So f comma g, this just means, this is just the notation for the inner product. This is the integral from A to B of f of x, g of x, dx. It's just the integral of the product. And it's easy to check that this inner product satisfies the following sort of very natural conditions. You learn this in calculus, it's no different. So if you have the inner product of f and g and the inner product of g and f, they're the same. Of course, f times g is the same as g times f. And if you take f and the sum of two functions, the inner product is just f of g and the inner product of f and h. And if you have f and some constant alpha times g, you're just multiplying this by a constant. You can always take a constant outside an integral sign. So this is alpha times the inner product of f and g. So this inner product satisfies these properties. And so you can think of this as something analogous to like vectors. Like when you took Calc 3, you looked at two-dimension and three-dimensional space. You had an inner product of points, what we called vectors, in the two-dimensional space and the three-dimensional space. So these are just like vectors. And the length, or the norm of a function f, is just you take the inner product of f with itself and take the square root. So it's usually denoted like this. The norm of f, this is the square root of the inner product of f with itself, which is the square root of the integral from a to b, f of x times f of x is f of x squared dx. Any questions about this? Let's look at an example. Suppose we take the interval 0 to 1, and we take, let's say, f of x equals x cubed, and g of x equals 1 plus x on the interval 0, 1. So the inner product of f and g is the integral from 0 to 1, f of x, g of x, dx. That's the integral from 0 to 1, x cubed times 1 plus x, which is the integral from 0 to 1 of x to the 4, x cubed plus x to the 4th. And if you do the integral of x cubed is the 4th, the integral of x to the 4th is the 5th. You add them up, you get 9 over 20. So the inner product of these two functions is 9 over 20. And the length of the function f, well, the length squared is the integral from 0 to 1 of f of x squared dx. That's the integral from 0 to 1 of x cubed squared dx. That's the integral from 0 to 1 of x to the 6th, which is 1/7. That's the norm squared. So the norm of f is 1 over the square root of 7. So this is just simple calculus. So if we keep in mind the sines and the cosines as the model, which we're generalizing, we say that a sequence of functions, f1, f2, f3, and so forth, on an interval from a to b is orthogonal if, when you take the inner product of fi and fj, that's equal to 0 for I different from j, and the inner product of fi with itself, which is just the norm of fi squared, is not 0. So that's what it means for a sequence of functions to be orthogonal. And an orthogonal sequence is called orthonormal if the norm of each function is 1 for all I. So the example you know best is in the plane. Let's just look at vectors. If we take the vector e1 to be 1, 0, and the vector e2 to be 0, 1, and whenever we have two vectors, let's say v1 is x1, y1, v2, x2, y2, we define the inner product v1, v2 to be x1, x2 plus y1, y2. So you saw that in Calc 3. The inner product of E1 and E2 is 1 times 0 plus 0 times 1 is 0. The inner product of E1 with itself and the inner product of E2 with itself is 0 squared plus 1 squared is 1. So these two vectors, E1 and E2, are orthonormal. each has inner product with the other equal to 0, and the length of each is equal to 1. Any questions about this? So the general question is the following. Suppose that Fn is an orthogonal sequence of functions. On an interval from A to B. So let f of x, f, I often don't bother to write the parentheses around the x. This is just a function. Be a function on the interval from A to B. And the question is always, can we write f of x as some infinite series, constant Cn times Fn of x, n equals 1 to infinity, for some constants, real numbers, C sub n? That's the question. Now, another way to pose this question is to consider the partial sum, right? So this is just what you learned about in calculus. Suppose we let S sub capital N of x be the sum of the first capital N terms of this series. We want to know how well does Sn of x approximate the original function. And in what sense does the infinite series, this is the infinite series, f of x equals summation Cn f sub n of x, and goes from 1 to infinity. How much, in what sense does this infinite series converge to f of x? And the text gives 3 different ways to understand, or 3 different kinds of possible convergence, each of which is important, and I will describe them right now. So we have f of x, and we're comparing it to this partial sum, and goes from 1 to capital N, C sub n, f sub n of x. So this is a partial sum of the infinite series. And how close are these? In what sense? So we have 3 different ways to compare these two. The first is the pointwise error. So for each point x, we can define the error, capital E of n of x, to be the difference between f of x and this partial sum. And we say that the infinite series converges pointwise to f of x if this error, E sub n of x, goes to 0 as n goes to infinity. So if these partial sums converge pointwise to the function, then we say that we have pointwise convergence. So that's one way to understand convergence of a Fourier type series to a function. We also have what is called the mean square error. Right? Remember, the pointwise error was this. It's the difference between f of x and Sn of x at each point. The mean squared error is a kind of average error. We'll write a lowercase e sub n. And what we do is we look at this pointwise error. It can be positive or negative. We don't want positive errors and negative errors to cancel out. So the easiest way to do that is to take the square and integrate that or average that from A to B. So this is what is called the mean square error. It's kind of an average of the error. And we say that the infinite series converges to f of x in the mean square sense if En goes to 0 as n goes to infinity. So if this mean squared error goes to 0, then we say that the infinite series converges in this mean square sense to f of x. And this is very different from pointwise convergence, and neither one implies the other. So you can have a series that converge pointwise, but not in the mean square sense, and series that converge in the mean square sense, but not pointwise. And we have a third notion of convergence, which is uniform error, uniform convergence. So what is called the uniform error, which we write as little epsilon sub n, is the following. We look at the pointwise error, f of x minus Sn of x in absolute value, and we ask for the largest this can be, the maximum for any x between A and B. So we say that the infinite series, remember, summation Cn Fn of x converges uniformly to f of x if the limit of en goes to 0. I mean, there's a very pretty way to picture what uniform convergence looks like. Suppose we have the interval from A to B, and in that interval, let's say this is the graph of y equals f of x. If you take any epsilon neighborhood of this, so this is epsilon, then Sn of x is always in this little thin strip around the curve. So whenever you have convergence, uniform convergence, you certainly have pointwise convergence, but the opposite doesn't hold. The opposite statement isn't always true. So let me do an example of these three types of convergences. Suppose we take the series summation minus 1 to the n, x to the 2n, as n goes from 0 to infinity. This is for x between 0 and 1. Now this series converges. I can write this as summation n goes from 0 to infinity minus x squared to the n. And you learn in pre-calculus that this geometric progression converges to 1 over 1 plus x squared. So this is my function f of x, and my partial sum, Sn of x, this is the sum, n goes from 0 to capital N, minus 1 to the n, x to the 2n. Let's see, what is this? This is, again, n goes from 0 to capital N, minus x squared to the n. So this is a finite geometric progression. And you also learned in pre-calculus what this is equal to. This is 1 minus x squared to the n plus 1 over 1 plus x squared. So that's equal to, I have 1 plus x squared, 1, I have x to the 2 times n plus 1. And here I have minus 1 to the n plus 1. So 1 plus minus 1 to the n, or n plus 2, but minus 1 squared is 1. This is what we get. So let me just write this on a clean piece of paper. So we have the function f of x, which is 1 over 1 plus x squared. And we have the infinite series, summation n goes from 0 to infinity, minus 1 to the n, x to the 2n. And the nth partial sum of that series is just the sum from 0 to capital N, minus 1 to the n, x to the 2n, which I just calculated is 1 plus minus 1, x to the 2, n plus 2, over 1 plus x squared. And for x between -1 and +1, x to the 2n plus 2 goes to 0 as n goes to infinity, right? So the limit as n goes to infinity of Sn of x is the limit as n goes to infinity, 1 plus 1 minus 1 to the n, x to the 2n plus 2 over 1 plus x squared. This term goes to 0, so this limit is 1 plus x squared, which is f of x. So summation n goes from 0 to infinity, minus 1 to the n, x to the 2n, does converge pointwise to f of x. So we have pointwise convergence. What about uniform convergence? So remember, in uniform convergence, we look at the maximum difference between f of x and Sn of x. So we have epsilon n is the maximum, in this case for x between -1 and +1, of f of x minus Sn of x. Well, remember, Sn of x was summation from 0 to n minus 1 to the n, x to the 2n. That was equal to 1 plus minus 1 to the capital N, x to the 2 times n plus 1 over 1 plus x squared. And f of x is 1 over 1 plus x squared. So if we look at f of x minus Sn of x, that's, or let me do it in the opposite order just to avoid a minus sign. We're taking absolute value, so it doesn't matter. Sn of x minus f of x in absolute value, that's 1 plus minus 1 to the n, x to the 2n plus 1 over 1 plus x squared minus 1 over 1 plus x squared. These cancel. This is minus 1 to the n, x to the 2n plus 1 over 1 plus x squared, which is x to the 2 times n plus 1 over 1 plus x squared. What's the maximum of this? So as x goes to 1, this goes to a half. So the maximum between minus 1 and plus 1 of Sn of x minus f of x, that's a half for all n. So therefore, epsilon of n as n goes to infinity isn't 0. So we do not have uniform convergence. We don't have uniform convergence. What about the third type of convergence, mean square convergence? So in this case, we need to look at capital E sub n, which is the integral from -1 to 1 of Sn of x minus f of x squared. Well, I already calculated Sn of x minus f of x. This is the integral from -1 to 1. Right? Here's where I calculated it. It's x to the 2 times n plus 1 over 1 plus x squared. This is x to the 2n plus 2 over 1 plus x squared dx. So this is the integral from -1 to 1. X, I square this, I get 4n plus 4 over 1 plus x squared dx. And let's do some elementary calculus. 1 plus x squared is always at least 1. So 1 plus x squared is always at least 1. So 1 over 1 plus x squared is less than or equal to 1. And so x to the 4n plus 4 over 1 plus x squared is less than or equal to x to the 4n plus 4. Just multiply this by x to the 4n plus 4. So this integral was less than or equal to the integral from -1 to 1 of x to the 4n plus 4 dx, which is 1 over 4n plus 5, x to the 4n plus 5, evaluated from -1 to 1. This is an odd power. -1 to that is -1. So this is equal to 2 over 4n plus 5. So this mean squared error is bounded above by this, which means the limit of En as n goes to infinity is 0. And so we can say, yes, we do have mean square convergence. And in the study of differential equations and more generally mathematical analysis, these three kinds of convergence, especially mean squared convergence, are very important. They're very useful. And one reason we'll see right now why it's useful, we're not going to prove the theorem. Of course, that's more for a course in Fourier series. But so let's suppose Fn is an orthogonal sequence of functions and there exist constants Cn such that some function f of x is this infinite series Cn Fn of x. And this, for this choice of these Cn's, this converges in the mean square sense. So we're not assuming pointwise convergence or uniform convergence, just this mean square convergence. And in that case, we can interchange summation and integration. And we see exactly what we saw for the case of sines and cosines. If we take the inner product of f with fm, and that's the integral from a to b of f of x, fm of x dx. That's the integral from a to b of, let's say, fm of x times f of x, which is summation Cn Fn of x dx. Interchanging summation and integration, I get summation and goes from 1 to infinity, C sub n, the integral from a to b of Fm of x, Fn of x dx. These are 0 except when m equals n. And so when n is equal to m, I get C sub m, the integral from a to b of Fm of x times itself squared, which is Cm times the length or the norm of Fm squared. That's what that integral is. So Cm is 1 over the norm of Fm squared times the inner product of f with Fm. So if you have mean squared convergence, then you can write these coefficients by this classical formula. And if the sequence Fn is orthonormal, then the norm of Fm is always 1, and Cm is just the inner product of f with Fm. Okay. Any questions about this? This is all, I'm trying to follow as closely as I can Logan, the book, because this chapter is, I think, very clearly written. And the great property of these Fourier coefficients is the following. So this is in the text, Theorem 3.8, which is called best approximation. And what it says is the following. So that Fn be an orthonormal sequence of functions on the interval from a to b. Let Cn be the sequence of Fourier coefficients of f. So that means Cn is the inner product of f with fn, which is the integral from a to b, f of x, fn of x dx. Let an be any other sequence of numbers so if you look at the mean squared error between f and the partial sum of the Fourier series, and if you look at the difference between f and the partial sum of any other linear combination of the functions fn, let's square it to make it easier. We have inequality. That is, the Fourier series is always the best approximation. The partial sum of the Fourier series is always the best approximation to your function. No other linear combination can approximate it better. So this theorem I want to prove, and it basically is a nice algebra calculation. So let me do it on, let's see if I can get it on one sheet of paper. So what we want to prove is that the mean squared error of the Fourier series is never bigger than the mean squared error of any linear combination of your functions f sub n. So the proof is a nice calculation, which goes as follows. So I should say this is nothing. This is the theorem, and this is the proof. If I take f minus summation an fn and square it, square the norm, this is the integral, or this is, forget that, this is the inner product of f minus summation an fn with itself. The norm squared of a vector is the inner product of the vector with itself. This is the vector. And I can use the linearity property of the inner product. I can expand this as follows. I'll do it in two steps. This is f minus summation an fn, n goes from 1 to n, inner product with f, minus f minus summation an fn, n goes from 1 to n, inner product with this. So is this inner product with f and this inner product with this. It's this inner product with f minus this inner product with this. And this minus this inner product with f, this is f comma f minus the inner product of these two, summation an fn inner product with f, minus this inner product with this, f summation an fn, and this inner product with itself. I'm putting in more steps that are in the book just to try and make it a little bit clearer. So this is f inner product with itself minus, this is summation, n goes from 1 to infinity. Inner product of fn and f is the same as the inner product of f with fn, but it's symmetry. Here I get the same thing again exactly, so I have two of them, this and this. I can put a 2 there. And then here I have this double sum. Let me write this as m goes from 1 to n goes from 1 to n. So this is a double sum am an inner product of fm and fn. But this is 0 if m is different from n, and it equals 1 if m equals n. So I'm only summing over the terms where m equals n, so I get inner product of f with itself minus 2 times summation an f comma fn, and here I just get summation a sub n squared. Inner product of f with fn is cn. So cn is the inner product of f with fn. This is the Fourier series. So this is inner product with f minus 2 times summation n goes from 1 up to n, an times cn, plus summation an squared and I want to add summation cn squared, but then I have to subtract it. Right. That is, I'm just adding 0. But when I do that, this expression is the following. I get inner product of f with f minus summation cn squared, and this is summation n goes from 1 up to n, an minus cn squared. And this see, here the ANs are any constants at all. If I picked AN equals CN, this will be 0, I would get this. So this expression is F minus summation CN Fn squared plus summation AN minus CN squared. And this is a sum of squares, it's non-negative. So I only get something smaller if I throw this away. And what I get is f minus summation Cn Fn norm squared. So this is the best approximation theorem, 3.8 in the notes. And this is true. This is the best approximation theorem for Fourier series. Or more generally, if you have any orthogonal sequence of functions on an interval AB, any orthonormal sequence of functions, and you write down the Fourier coefficients, so Cn is the inner product of f with Fn, this mean squared error is the smallest, is always less than or equal to any other series you can construct using those terms. And what we proved one step in the proof was that the norm of f minus summation and goes from 1 to n, Cn Fn squared, that's the same as the norm of f squared minus the sum of the squares of the Fourier coefficients. And this is a square, so this is greater than or equal to 0. So this means summation and goes from 1 to n, Cn squared is always less than the norm of f. And this is true for all n. So this tells us that if we take the infinite sum of these Fourier coefficients squared, infinity, the infinite series is less than the norm of f squared. And this inequality is called Bessel's inequality. All right. So again, everything I'm doing is in the text, and it's very neat and clean and easy to read. Yep. Okay. And I just want to make one last remark, and then we're in pretty good shape. So this is definition 310 in the book. An orthonormal system of functions, Fn, is called complete if the following is true. For every function f which is not identically 0, there is some n, at least one, such that the inner product of f with Fn is not 0. So the only function which has all of its Fourier coefficients equal to 0 is the 0 function. And there's a theorem, which I'm not going to prove. It's not hard. It's called Parseval's equality. So we already showed Bessel's inequality, that summation n goes from 1 to infinity, c sub n squared is always less than or equal to the norm of f squared. Parseval's inequality says that these are equal if the sequence Fn is complete. Okay. All right, so I just covered a decent amount of material. It may be if you had taken linear algebra, or if you had taken a course in ordinary differential equations, or a course in analysis of any sort, you will have seen some of this, not necessarily all of it, but I'm assuming that no one has seen any of it, and that's why we're doing it all from scratch, as does the textbook. So okay. Monday is the exam. There's no class next Wednesday. CUNY is closed for Thanksgiving weekend, a long Thanksgiving weekend. So the exam is Monday. The next class is a week from that Monday. There will be homework for that Monday when you come back on material that I covered today. I'm also going to have a review class on Friday of this week at 11 o'clock on Zoom. For any questions you might have about material that's being covered on the exam, characteristics and Laplace transform, convolution, and so forth. So I'll send out an email, but there will be a review class on Zoom from 11 to 12 on Friday for anyone who's available. And if you have other questions, you can just email them to me, and I'll try to answer in any way that I can. Questions about any or all of this? Let's see. Yes, I will send you the link. I'll send you the link. It's probably the same link as I'm using for this course that you logged in. It'll be the same link that you use for the Monday, Wednesday, 11 o'clock classes. I'll make sure that that works Friday at 11 as well. Okay. Anything else?